one. This is the review I posted on D2L. So let's see how it goes. You're given a bunch of reactions, 3 reactions. They're asking you which of these reactions would you expect to be exothermic. Okay, so yeah, let's look at reaction A. Reaction A, you're going from some AA bonds to all AB bonds. Okay, meaning you're going from weaker bonds, which has a higher potential energy, to stronger bonds, which has a lower potential energy. Meaning, when you go from reactants to products, the energy has to be released because you're going from high energy to low energy. Okay, so exothermic means you are going from higher energy reactants to lower energy products. Okay, so this is the reaction path, and this is potential energy OH. Okay, so reaction A definitely satisfy that. And reaction B, you're going from all AB on the reactant side. These are all AB, which is stronger. Therefore, it's going to have a lower potential energy. Again, the mantra is the stronger the bonds or stronger the attractive interactions, the lower the potential energy. Okay. On the other hand, on the product side, we have some AA bonds, like in hydrogen over here, AA bonds. Okay, meaning you have weaker bonds on the product side, meaning higher potential energy. So in that case, we are going from lower potential energy to higher potential energy, and it needs to be absorbed, meaning it's an endothermic reaction, not exothermic. Reaction C, you are going from so in this case, what I would do is I would look at the ionic compounds, because ionic compounds tend to have the strongest bonds. Therefore, that's the first thing I'm going to look at. So we have a compound here, Fe2O3, which has a charge product of -2 for oxygen charge, and then the Fe charge should be +3. Okay, and how do I know that? Oxygen is in the 6th column or the 6th group, meaning it has 6 valence electrons. Therefore, it's going to gain 2 electrons, become like a noble gas, becoming a -2. If that is the case, my minus the negative or the anion side is -2 times 3, -6. Okay, therefore the cation side should be +6 for us to have a neutral compound. +6 divided by 2, because we have 2 Fe ions, is +3, and that's how we got that. And therefore the charge product is 6 here. Okay. On the other hand, we don't have ionic compounds on the product side. We have covalent compound, carbon dioxide, then we have Fe metal, which has metallic bonds. But ionic bonds are the strongest. Therefore, I would say in option C, we are going from lower potential energy on the reactant side because of strong ionic interactions to higher potential energy on the product side, meaning it's an endothermic reaction. Therefore, the correct answer must be option A. Only reaction A is exothermic. Okay, so the next one, the following chemical reactions are blah, blah, blah. Okay, it's the same thing. Which of these reactions would you expect to have a delta S greater than 0? Okay, so we're talking about the entropy here. When it comes to entropy, we know the gases call the shots. In reaction A, we are going from 25 gas molecules to only 16 gas molecules. Okay, this is 16 gas molecules, meaning we are decreasing the number of configurations because we have less gas molecules in the on the product side, meaning delta S is negative for this reaction A. Okay, for reaction B, we are going from 3 gas molecules on the reactant side to 5 gas molecules on the product side, meaning we are increasing the entropy, meaning S is increasing. Therefore, delta S is positive for reaction B. For reaction C, we are going from 3 gas molecules to 3 gas molecules. You can see 3 over here and 3 over here. But on the product side, the gas molecules are more complex. Actually, you know what? I take that back. Gas molecules have a higher mass because after after considering the phase, the second criteria we are going to look at is the mass of the gas molecules. Because the gas molecules have a higher mass on the product side, the product side has a higher entropy or higher number of configurations. Therefore, in reaction C, you're going from low to high number of configurations, or low to high entropy. Therefore, entropy is increasing, or delta S is positive. So reactions B and C, you have a delta S greater than 0. Right, moving on to the next question. Okay. Let's do this. Okay. Which of these reactions would have Peg diagram as shown to the right? So in the Peg diagram, the products have a lower potential energy. Therefore, it cannot be B, because products have a higher potential energy, and it cannot be C as well. We decided on that. Okay. Because okay, so it has to be A. I mean, just by looking at it, it has to be A. But let's consider the other ones as well. So products have a lower potential energy and a lower number of configurations, and reaction A satisfy that. Okay. Because you have less gas molecules on the product side in reaction A, meaning we are going from a higher number of higher entropy to lower entropy. Okay. Therefore, the products have a lower entropy, and also products have a lower potential energy because you have stronger bonds on the product side in reaction A. Therefore, I would select reaction A as my answer. All right, moving on. Which of these reactions would be product favored at all temperatures? Oh, none of them. Okay. Why did we say that? Okay. So for reaction A, so we decided that our Peg diagram is this, right? If this is the case, products are favored only by the potential energy, and as a result of that, this is product favored only at low temperatures. Okay, and the other reaction, products have a higher potential energy. Okay, therefore the products are not favored by the potential energy. Therefore, it's not going to be always product favored. But if you quickly plot the Peg diagram for reaction B, products have a higher potential energy and a higher number of configurations because you have more gas molecules. Therefore, you should have something like this for the HS diagram or the Peg diagram. Okay, so this is product favored. Reaction B is product favored only at high temperatures. And then the other reaction, reaction C, which is not an option anyway. Okay, so reaction C, you're going from lower potential energy to higher potential energy. The products have a higher potential energy, and also products have a higher number of configurations as well. So this is actually for reactions B and C. The Peg diagram is this one over here. Same thing. So none of them is always product favored. Okay, so one of reaction A is product favored only at low temperatures, while reactions B and C are product favored only at high temperatures. Okay, moving on. Which of these reactions would exhibit delta G versus temperature graph, like the one shown to the right? Okay, so we decided the reactions B and C. I mean, there are different ways of approaching this, but we already decided that these two reactions are product favored only at high temperatures. Why? Because they had a Peg diagram that looked like this, right? So meaning at high temperatures, delta G is negative, because remember that you have this clearly in your notes as well. If it is product favored, then delta G is negative. Okay, so if product favored only at high temperatures, you see that as the temperature increases, it increases beyond this temperature over here, which we call the switching temperature. The delta G becomes negative, meaning at high temperatures, the reaction is going to become product favored. At low temperatures, on the other hand, delta G is positive, meaning it's reactant favored. Therefore, it should be both B and C for this. Right, moving on. Which of these reactions would have an equilibrium constant greater than 1 only at low temperatures? It should be reaction A, right? So reaction A, we decided it is product favored only at PF, product favored only at low temperatures, meaning at low temperatures, the should look something like this. Okay, so here's the temperature axis, and then here's my K, and here's my 1. At low temperatures, the K is greater than 1. And at high temperatures, K is going to become less than 1, meaning it's going to become reactant favored. Okay, so this is by definition product favored only at low temperatures. Okay, so K is greater than 1 only at low temperatures should be option B, option A only. And then moving on to next question. Determine the standard enthalpy change for reaction D. Oh, reaction D is given. It's kind of a decomposition. Okay, so it tells us that we break bonds. Even though calcium oxide seems to have strong ionic interactions, it's a decomposition, so it's a bond breaking. So anyway, I predict this is to be endothermic reaction, but anyway, let's see how it goes. So delta H reaction. Delta H reaction is sum of delta H formation for products minus sum of delta H formation for reactants. Okay, so the products, we have calcium oxide and CO2, 1 mole each, so which is great. We have 1 mole of CaO. CaO has formation enthalpy of minus 635.1 kilojoules per mole. To this, we need to add carbon dioxide, which is, oh, not this guy over here. We have 1 mole of minus 393.5 kilojoules per mole. Okay, these are my products sum. From this, we need to subtract the reactant, which is calcium carbonate, which has this value over here. Okay, so we have again 1 mole multiplied by minus 1206.9 kilojoules per mole. Okay, so I'm getting tight over here. Then moles cancel out cases, and we're going to be left with minus 635.1 plus minus 393.5. Okay, and minus negative 1207.06.9. Okay, all of these are in kilojoules. All right, so if you add these up, let's see, 635 plus 300 is 935, 935 plus 90 is 1025, 1028, 1028.6, I think, without a calculator. Let's see. I mean, I'm going to run this anyway. Plus, then we minus negative 1206.9 means plus 1206.9 is a positive value. So I think it's going to be 71.4. 171.4, 177.4, 170.4, 170. 8.3 or something like that, which is this value over here. Okay, I did this in my head. You don't have to do this. You use a calculator and check. Okay, so these are the numbers at least. I mean, if you plug and check these values, you should get positive value. I think. Okay, so I got option B. All right, moving on. Estimate the temperature at which the directionality of reaction D reverses. Okay. All right, done. Okay, now here's the thing. For this to happen, we need to get the delta H and delta S, right? So we have delta H to be equal to 178.3 kilojoules. And we need to calculate delta S as well. Unfortunately, I mean, it's the same calculation as before, plus temperature. That's the way it is. Okay, delta S reaction. I wish I think should make some room here. Delta S reaction standard conditions should be sum of standard entropy values for the product minus sum of standard entropy values for the reactant, which is going to be equal to these guys. Calcium oxide is 38.2, 30. I just want to do it correctly. So we have 1 mole of CaO multiplied by 38.2 joules per mole per Kelvin. To that, we need to add 1 mole of carbon dioxide, which is calling the shots, 213.8 joules mole per Kelvin. Okay, these are my products. Minus, we need to subtract the reactant, which is calcium oxide, which is 92.9. 1 mole times 92.9 joules mole Kelvin. All right, now switching back to do moles cancel out. Okay, and then what do we get? We get 38.2 plus 213.8. 213.8, 243.8, 243.8, 251.8, 252, I think 252 joules per Kelvin for the product side, minus for the reactant side we have 93 or 92.9 joules per Kelvin. Okay. Now this should be close to 7.1, 159.1, I think, 159.1 joules per Kelvin. So this is equal to 0.1591 kilojoules per Kelvin, because it's important that we have delta H and delta S in same units, comparable units. Okay, so we know at the switching, so delta G is equal to delta H minus T delta S at the switching temperature. Okay, at Ts, delta G is equal to 0. Delta G is equal to 0 equal to delta H minus Ts delta S. Therefore, this gives us Ts to be delta H divided by delta S. Delta H by delta S. Okay, so we have 178.3 kilojoules divided by 0.1591 kilojoules per Kelvin. You're gonna get the answer in Kelvin. For that, I need a calculator. Let's see if I can find one on my phone. Okay, let's see. I have a phone. Okay, I have 178.3 divided by 0.1591. Got 1,120.7. Okay, that is closer to C. I'm glad that I at least got something closer. But anyway, again, Except for the division, I did everything in my head, but you should use the calculator and make sure that you get the same number. But this is the way. All right, moving on to the next question. Similarly produces at temperatures close to blah, 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 Celsius. What is the value of the equilibrium constant K for reaction D under such conditions? Goodness gracious. Okay. Now, to do this, okay. I'm just checking if there are any shortcuts here, but it's okay. So the idea is we need to get the delta G first. This is brutal. Delta G at this temperature. So with this equation, delta G is equal to delta H minus T delta S. And then this gives us delta H. See, we calculate delta H somewhere. Yeah, delta H was 178.3 kilojoules. 178.3 kilojoules minus temperature is in Kelvin though. Okay, this is in Celsius. You need to convert this to Kelvin. So you need to add 273 to this. That will give us 1617. I want to say 23 Kelvin. Okay. Okay, let's run with that. 23 Kelvin. And delta S we calculated to be 0.1591 kilojoules per Kelvin. Okay, so Kelvin cancels out. We have everything in kilojoules, so this is gonna be, all right, I need a calculator. We have delta G to be 178.3 kilojoules minus let's see, okay, let's do 1723 multiplied by 0.1591. 273. No, 274. 274.1 kilojoules. Small 3 actually, but it's called it more kilojoules. Okay. Oh wow. I didn't expect that. Anyway, so now you see that this is going to become a negative value. Okay, so no, this is negative. Yeah, let's do that. So delta G should be equal to 178.3 minus 274.1. That's the issue with the calculator. Once you start using it, you want to keep using it, you know. You are switching off your brain. 95.8 kilojoules. Okay, we got that. And then what we're going to do is we know that delta G is equal to minus RT L natural log of K. Therefore, ln K is equal to delta, oh shoot, is equal to delta G divided by RT, should be minus sign. Okay, therefore, K is equal to e to the power of minus delta G over RT. Okay, so let's plug and chunk these numbers. Minus RT. Okay, anyway, so this is a negative value over here. Okay, so negative times negative. So let me write that. Negative times negative 95800. I just multiply by 1000 to make it joules. Joules divided by R, which is 8.314 joules mole per Kelvin. and then multiply this by the temperature, which is 1723. Oh my goodness, I need a scientific calculator to do this step now, but I don't know what the Apple does have it. Anyway, so this should be e to the power of plus, because negative times negative is positive. 95,800 divided by, I'll do the chunks, which I can do. 8.314 multiplied by 1723. Okay. 14,325. So you see that units cancel out nicely, cancel. Okay. All right. So what we want is 95,800 divided by 14,325 is 6.68. Okay, e to the power of 6.6. Let's call it 69. Now, okay. All right. So when I turned my phone, I mean, it went to the other way. But anyway, you guys should be using a scientific calculator for this. And then I took the exponent of 6.69, gave me something close to 805. 802 on my calculator on my phone, but anyway, I think it is close enough. That's the closest one we have. All right, so let's see. No, keep going. Okay, let's move on. Which of the following expressions represents the equilibrium constant K for reaction D? Okay, so equilibrium constant expression do not have solids or liquids because their concentrations are constant during the reaction. Okay, so the only thing that we're going to have is, so remember, K is products over reactants. Our products, only products I'm going to include a CO2. K should be CO2 gas concentration times calcium oxide is not included because it's a solid, divided by calcium carbonate concentration, which is a solid, that's a constant as well. Okay, so the only answer should be option C over here. All right, moving on. Question 11, which of these statements is true? Reaction is exothermic. Okay, you are given the data. Okay, the thing is, when you are given the data, you should use the data. Reactants in reaction E can adopt more configurations. That's true. Yeah, so you said this is okay. Let's forget about the statement A, option A for the moment. Option B says the reactants in reaction E can adopt more configurations than products. That is true because we have a gas on the reactant side. You know, when it comes to number of configurations, gas is called the shot. So this is absolutely correct. More H2CO3 will form at low temperatures than at high temperatures. Okay, so I have a feeling this is all of the above by predicting without using the data, because they're not asking you to use the data here. Okay, you can use the data as well. Anyway, so we can predict this to be an exothermic reaction, meaning products have a lower potential energy. If products have a lower potential energy, then more products will be formed at low temperatures than at high temperatures. That is correct as well. If that is correct, the only option I can select is option D as my correct answer. All of the above. Reaction is exothermic. Okay, again, we are making bonds. Okay, making bonds is exothermic or releases energy. Therefore, this should be correct as well. We already did a lot of calculations with delta H and delta S already. I mean, I don't feel like we should do it. But if you do it, you will see that delta H value should be negative here. Okay. Moving on. Which of these statements is true? Reaction E is product favored at 25 degrees Celsius. Okay. Now, yeah. So this is product favored only at low temperatures because energetics favors the products and entropics favors the reactants. Okay, meaning a diagram is going to look like this. Okay. So we need to use the data to do this. I think the best thing to do is I hope that we're not going to see this many calculations. That it takes some time. But let's do this. Okay. All right. Let's see. So delta H for this reaction is products minus reactants. Product is H2CO3. H2CO3 is minus 698.7 kilojoules per mole. So let's say the moles cancel out because this is 1 mole. And minus, then we have the reactants. CO2 is 393.5 minus 393.5 plus H2O minus 285.8. Okay, so if you do that, you have minus 698.7. This should be a positive value. Positive 393. Oh goodness. Yeah, you know what? This is a calculator, why not? 393.5 plus 285.8. 679. 679.3. Okay. So therefore the difference is I think we can do this in our head. So we have 0.7, okay, 10.7, 18.7, 19.4, I think. Minus 19.4. You know what? Let's do this. I'll check. Because I'm so used to the calculator on my phone now. I don't feel like doing this in my head, even though I did it. 679.3. Yep, 90.4. Good. Yeah, so we got it. Anyway, so this is kilojoules, negative. And delta S now. Delta S, let's have a different color for the sake of it. Okay, green. Delta S is again products minus reactants, so it's standard entropy is these guys over here. So our product is 191 joules per Kelvin, minus our reactants are CO2, which is it's called the shots 213.8 joules per Kelvin, plus 70. H2O is 70, liquid is 70 joules per Kelvin. Okay, more, it's only 1 mole. It cancels out. Okay, so if you do that, we have 191 joules minus, we have 283.8 joules per Kelvin. Okay, obviously it's going to be a negative value. It should be 9. 9 plus 83 is 92.8, I think, minus 92.8 joules per Kelvin should be our delta S reaction under standard conditions. So let's check again. 191 minus 283.8. It's minus 92.8 joules per Kelvin. But okay, now we got that much. And now what we're going to do is, we know the switching temperature is Ts delta H over delta S. Delta H is minus 19.4 kilojoules divided by minus 0.0928 kilojoules per Kelvin. Note that I converted joules to kilojoules for delta S. Otherwise, I mean, I cannot deal with this, right? Anyway, so the kilojoules cancel out. You're going to get the answer in Kelvin, and the negative divided by negative is positive. So that is going to be, let's see, 19.4 divided by 0.0928 is 209. 209.05 Kelvin. Okay, so in Celsius, and this is Kelvin. So in Celsius, this, you know what, you can do that way as well. So 25 degrees Celsius is 298 Kelvin. Okay, and then we know this is product favored only at low temperatures. Okay, so because 298 Kelvin is greater than 209.5, so let me actually draw it like this to make more sense. Let's do the delta G versus temperature graph. Okay, this is product favored only at low temperatures, so it should look something like this. And then what we know is this temperature over here is 209 Kelvin. Okay, and then 298 Kelvin is what is given to us in the question, is over here. This is our 298 Kelvin. Okay, at 298 Kelvin, the value of delta G is this much, which is a positive value. Okay, if delta G is positive, it's going to be reactant favored. So reaction is reactant favored at 25 degrees Celsius. So yeah, this should be, use a different color. The answer should be reaction option B. Right? We calculated a switching temperature, and then based on that, 298 Kelvin, delta G is positive. All right, moving on to question 13. Let's see, I have office hours in about 5 minutes, so I need to make sure that I complete next 4 questions in 5 minutes. Let's see. As the temperature of the oceans increases due to global warming, which of the following statement is true? The dissolution. So yeah, carbon dioxide is dissolving in H2O. This is what is happening here in this reaction, right? So we know when you increase the temperature, the amount of carbon dioxide that dissolves should be less, because we know at temperatures above 209 Kelvin, based on our previous question, the reaction is reactant favored. Okay, so dissolution should be less. Okay, let's look at the options. Global warming. What does global warming does to the dissolution of carbon dioxide? The dissolution of carbon dioxide in water, as represented in section E, is more likely to happen. No. When you increase the temperature, no. Dissolution will not be affected. No, it will be affected. Dissolution of CO2 in water, as represented in E, is less likely to happen. Yep. Option C, not enough data. No, it's enough data. Okay, so yeah, because when the temperature is high, the amount of carbon dioxide that it dissolves, so the reaction that is occurring here is going to be less and less. More reactant favored as possible. More reactant favored. Okay, that's the idea. Okay, so option C is the correct answer there. Which of the following graphs best represents the concentration and H2O CO2 and H2CO3 as a function of time as reaction reaches equilibrium? 25 degrees Celsius. At 25 degrees Celsius, we decided the reaction is reactant favored. Okay, where did we do it? Yeah, here, right? Reaction is reactant favored. Delta G is positive. Therefore, we should have more reactants than products. Okay, so not A, because A has more products, not B, because they are equal amounts at the equilibrium. C looks really good. And D is crazy. It has not reached the equilibrium. Okay, option C is the correct answer there. All right, moving on to question 15. Oh, we only have 15 questions. Great, we're done. So which of the following graphs represents the variation of the equilibrium constant K with temperature for reaction E? Oh, this is simple because this reaction is product favored only at low temperatures, meaning at low temperatures, here's my temperature, here's my K, here's my line at 1. At low temperatures, the reaction has K value greater than 1, and at high temperatures, it should be less than 1. It should look something like that. So that should be option A. All right, so that's all the time I have. We covered the multiple choice questions. In a separate video, I'll go over these pre-response type questions. Okay. All right. I'll see you guys in class. Bye, everybody. Let's see.